Hello everyone, good afternoon. I'm Suparna Ghanvatkar. I'm a second year PhD student under Prof. Bhavrajan, and today I'm going to talk about risk prediction in intensive care units. Let us look at why do we need to care about intensive care units. Let's consider the situation of Italy during February to July 2020, that's during this COVID-19 pandemic. The graph plots the number of patients admitted into the ICU and the number of deaths recorded per day. We see as the ICUs reach their capacity, that is, the number of patients admitted into the ICUs reaches its capacity, we observe that there are more deaths recorded. Why does this happen? So there are a lot of problems which Italy faced during this COVID-19 pandemic, such as the ICU admissions were 12% of the total positive cases. That's a huge number of patients requiring intensive care units. In addition to that, these COVID-19 patients who were admitted were spending more than 15 days in the ICU, while the average length of stay of a patient in the ICU is 5 to 6 days. Together, this created a lot of burden on the ICUs and a very high patient to staff ratio. As the staff needed to be diverted from other wards, it left other wards to be understaffed as well. And in addition to all this, doctors had to choose who they provide attention and care to. So we can conclude that ICU management is very crucial during pandemics such as this. And the aim of ICU management is generally to maximize the life years they save. However, ICU management is not just crucial during pandemics, but is essential and critical during day-to-day functioning of the hospital as well. So ICUs typically house very costly equipment and highly trained staff. Uh, this implies that from an economic standpoint, a high occupancy of ICUs is desired. However, previous research has shown that high occupancy in ICUs leads to a reduction in the quality of care provided to the patients. Uh, we saw from the previous example as well that a higher occupancy of ICU shows a higher mortality rate of the patients. It leads to a very overstressed staff as the patient to staff ratio gets skewed. Similarly, as the quality of care reduces, the chances of readmissions and the number of readmissions into the ICU also increases. The ICU and the overcrowding in the ICU leads to having an effect on other departments such as the operation theaters and emergency departments as well. As the OTs generally prefer and prioritize patients from the ICUs, the high number and the high burden on ICUs implies that it results in long surgical waiting times for surgeries. So one of the methods of helping improve and helping manage the ICUs is performing risk prediction. So risk prediction is used to identify the severity of the patients for triaging the patients, such as typically a mortality of the patient or the high risk of the patient of developing some complication is identified, and this is used for triaging of the patients. Risk prediction also serves as an early warning system. Uh, it also helps in deciding hospital policies and uses and is very useful to manage various ICU resources. And from a research perspective, it is also used for identifying the value of novel treatments, interventions, and cohort selections for clinical trials. So one of the risk prediction tasks that I'm talking about, classically, mortality prediction and length of stay prediction are used for risk prediction and triaging of the patients. There are other risk prediction tasks such as readmission of the patients, which predicts the probability that the patient would be readmitted into the ICU. The decompensation means the deterioration in the state of the patient. Sepsis is a sequential organ failure complication which occurs quite frequently in a lot of ICU patients and is nowadays having a lot of focus due to this. So traditionally, as I mentioned, mortality and length of stay are used as risk prediction metrics. So there are existing traditional scoring criteria, which are rule-based systems designed by clinical experts such as Apache, SAPS, and many more. However, these scoring criteria are not calibrated to be patient-specific. So this is exactly where machine learning models can step in. Machine learning models help for more better patient-specific predictions as compared to these traditional scoring criteria. However, the task of applying machine learning to these risk prediction models is not very trivial. So we are faced with challenges such as the heterogeneity in the clinical data, the missing data in the clinical setting being informative, such as sicker patients are examined more frequently. And of course, the machine learning models need to provide explanations of their solutions to help the doctors make decisions. Let me elaborate on what is the heterogeneity in the clinical data. So typically, we can say that the clinical data comes from two data sources. One is the electronic health records. This records many identifiers such as demographics, laboratory results of the patients, the vitals measured by the nurses, the medications administered to the patients, as well as nursing notes taken down by the caregivers. On the other hand, bedside monitors are automated monitors which are connected to the patients, and they continuously record the physiologic signals of the patients as long as they're connected to the patient. So they typically record very high frequency signals such as ECG, which are at 125 hertz, or they also have per second and per minute signals such as the heart rates. This different data sources is not the end of the heterogeneity. All of these heterogeneous data sources also are present at different time resolutions. For example, demographics is a typically a static kind of data source, which is obtained from a patient only once. That is typically at the time of admission of the patient. The medications, on the other hand, are given to the patients as and when required. Similarly, the laboratory tests are requested as and when required, and this results in a sparse and irregular time series. The ECG, on the other hand, is a very high frequency signal as compared to all of these sparse time series, and it runs continuously over the entire duration of the patient's stay. So we focus on the task of predicting the in-hospital mortality of the patient. So we consider the 24 hours of ICU stay of a patient, and we try to predict whether or not the patient survives. So the state of the art for in-hospital mortality prediction has been obtained through LSTMs. So this benchmarking paper uses demographics and laboratory results and vitals measured by nurses. All of this data is available in the electronic health records. They do a missing value imputation of previous value being carried forward. So they do not handle the factor that the missing value in clinical context is informative. Another model, that is the MGP RNN, which is the multitask Gaussian process RNN, handles the informativeness of the missing data as well, doing the task of classification by using a multitask Gaussian process to perform the missing value imputations, and jointly performs the classification by using the RNN. It uses data sources from the electronic health record again. We hypothesize that using data from the bedside monitors, such as the ECG, along with this electronic health record, has some potential advantages. This provides complementary information about the patient. Also, importantly, the bedside monitor records automatically. So it's not dependent on the manual recordings by the clinical staff, which is the case, which is the scenario in case of the electronic health records. However, if we extend the NGPRNN to include this data source, that is the ECG, We observe that MJP-RNN, for MJP-RNN, it becomes computationally infeasible to model such a dense time series. So our architecture builds up on MJP-RNN and effectively tries to handle the dense time series of 120 of ECG, such as of a high frequency of 125 Hertz. Let us look at the intuition of multitask Gaussian process before we proceed. Let's look at a Gaussian process. So consider the regression task. We have these black points which show the recorded data points. So there are multiple functions that fit the data. A Gaussian process assigns a probability to each of the function that fits the data. So mean of this probability distribution gives a probable fit for the data. So if we have two independent time series, we can get the posteriors by running two independent Gaussian processes, and we can get our y1 and y2. However, if the two time series that we are interested in are dependent, running two independent Gaussian processes does not consider the covariance between these two time series. This is exactly where the multitask Gaussian process comes into the picture. It considers, it takes the input of n different time series, dependent time series, and gives us the outputs of y1 to ym. And so multitask Gaussian process models not just the covariance between the time points of a time series, but also across various time series. Let us go back to our problem of mortality prediction. So we are interested in using 24 hours of patient data and trying to predict the mortality, in hospital mortality of the patient. So at the end of 24 hours, so we consider an RNN. We have 24 time steps, one step for every hour. And at the end of 24 hours, we tried to do a binary classification, that is the mortality prediction of 0 and 1 of whether the patient survives or not. So what does MJP-RNN do? It takes the sparse time series, that is the laboratory readings or the vitals measured by doctors, and it models this, it runs it through the multitask Gaussian process, takes the posterior of the MJP at the time that we're interested in, that is at every hour, and gives it to the RNN that I mentioned, which runs for all the 24 hours. What is the benefit of using this? As I mentioned, MJP-RNN provides a principled approach to handling missing values and considers the uncertainty in the imputed values as well. So how do we handle the addition of dense time series in our model? So consider the similar hourly RNN which is running for 24 time steps. The input to our RNN is a concatenation of all of these four data sources that we're interested in. So we copy the demographics for every hour. We give the hourly input of the medications. The laboratory and the vitals measured are passed through a multitask Gaussian process, and a latent function at every hour is given as the input to our RNN. And as for the case of ECG, we consider the statistical aggregate to every second, and we run a per second level RNN, and the state of the RNN at the time point that we're interested in, that is at every hour. We take the state of this per second level RNN into this hourly RNN. So let's look at the bigger picture again. We have a ECG, which is running at high frequency. We have a per second level RNN, which models this ECG. Then we have the sparse time series of laboratory readings, and this is modeled through a multitask Gaussian process, and we obtain the latent function at the hour, the time point that we're interested in. This is together concatenated with the medications given in the previous hour and the demographics of the patient. So for every hour, at every time step of the RNN, this is the input that is given. So we run the RNN for 24 time steps, and for every time step, we give the input from the multitask Gaussian process and entire 24 hours duration. The ECG per second RNN also runs. So the data that we use is Mimic3 dataset and Mimic3 waveform dataset. These are both openly available datasets, and the Mimic3 waveform dataset is has the physiologic signals from the bedside monitors, and we consider the ECG2 waveform. We only consider the patients that are present in both the datasets. So together, after the pre-processing, we obtain 7,317 ICU stays, and out of which only 788 have in-hospital mortality. That's a class imbalance of about 10%. So we do 5-fold cross-validation, and to adjust for the high class imbalance, we do an undersampling of the majority class. The majority class in this case being the non-in-hospital mortality patients, that is the patients who survived. So we do an undersampling of this class using condensed nearest neighbor. The baselines and the models that we evaluate our model against are traditional classifiers such as KNN, SVM, and MLP. They do not model the temporality of the data, and they are given the input of only the statistical aggregates of all the data sources for the entire 24 hours duration. As for the LSTM and MGP RNN, they model only the sparse time series from the EHR data. As we mentioned that they cannot handle the high 125 Hertz frequency of the ECG data. The MTS-RNN, which is our model, uses data from EHR as well as the bedside monitor, and it has shown to significantly outperform the other models on F1 score using with a very good p-value. So we will only look at the evaluations of LSTM, MGP-RNN, and MTS-RNN, as the first three classifiers give very poor predictions. Let's consider the comparison between LSTM and MGP-RNN. We see that MGP-RNN performs better on AUC and AUPR, and we also know that MGP-RNN has a principled approach to imputation using a multitask Gaussian process, and this seems to be giving us better results on AUC and AUPR, which are typically used for comparing classifications and predictions in this setting. Next, if we compare this MGP-RNN and MTS-RNN, we see that MTS-RNN has an improved prediction performance for most of the tasks, and most importantly, it performs well on AUC, AUPR, and F1 score. I would like to mention that the sensitivity, that is the recall, is considered an AUC, AUPR, and F1 score as well. And this high sensitivity implies that there is a better identification of the high-risk patients, which implies that our model gives a better prediction performance. So in summary, we can conclude that we can say that the combination of electronic health records and the bedside monitors can improve risk prediction models. And also that using of multiple modalities of inputs, especially the bedside monitors, which has an automated input, not manual recordings by clinical staff, can potentially counter the biases in data inputs. In future, we would like to expand our work to include other data sources such as the clinical notes and the radiology data. We would also need to evaluate our model more rigorously for seeing how well it models the temporal gaps in the dense time series. We also need to explore and utilize the missingness patterns in the data more, probably in a more rigorous fashion. The MGP kernels can be further explored to provide personalization to patients, as well as for looking at a combination of knowledge-driven and data-driven approaches. So thank you for listening to my talk.